All right, so the purpose of this video is to go through the Momentum in Sports worksheet. The first part we're going to go through a little bit faster because it is a little more basic, but as we get into some of the harder things, we'll take a little bit more time. So here we go. The first question here is about pool. Billiards, you're hitting a cue ball, striking the two ball. It says that the player strikes the cue ball, which has a mass of 0.17 kilograms, so that it travels with a speed of 2.7 meters per second. So the first question is, how much kinetic energy does the cue ball have? Well, we know that kinetic energy is equal to 1/2 mv squared. And so I should be able to just put in the mass, which was 0.17, and the velocity, which is in 2.7 meters per second, and then square it just like that, and that should give me the answer. Now, as I'm typing this in, notice that the 0.17 was already in kilograms, which is SI units, and also the 2.7 was in meters per second, which is also SI units. It should be in SI before you do any of these calculations, but in this case, I get 0.6. I'm going to round it to 3 digits, so 620 joules, and joules is the units for kinetic energy, for any kind of energy. All right, the next question asks, how much momentum does the cue ball have? Well, you may remember that momentum is equal to mass times velocity. And I won't always do this, but you'll notice I'm putting little arrows or pointy things on top of my P and my V. The purpose of that is to remind me that those are vectors and that the direction or the positive or negative is actually really, really important here. Okay, so when I do my momentum, I'm going to take the mass, which we know is 0.17, and multiply it by the velocity, which is 2.7, and we're going to assume it's going in a positive direction to start with. And again, we just punch that in, and we get 0.459. So 0.459, and the units, remember the 0.17 was kilograms, and then the 2.7 was meters per second. So we don't actually have a special unit, like energy is joules. We don't have a special one for momentum, so we just leave it as kilogram meters per second. All right, now we move on to the collision. We see right here that the cue ball is going to hit the two ball, and as it does that, it does say, assuming the ball strikes straight on, so the two ball then should continue forward just like this. Now, in a collision, we know that momentum is conserved. As long as there's no outside forces, then our momentum before and our momentum after should be equal for the whole system. So before, we know that the cue ball had a momentum of 0.459. The two ball was at rest before it got hit. So if I were to do that MV, when I put the 0M for the V, I'm going to get 0 momentum there. So I know that the total is 0.459, and the units are still that kilogram meters per second. Okay, now after the collision, it tells me that after striking the two ball, the cue ball is now traveling with a speed of 0.4 meters per second. So I'm actually going to have to calculate that. But remember, it's just mass, which was that 0.17 for the cue ball, times its new speed, which is 0.4. Notice that it says in the same direction as before. That's important because we said our direction before was the positive direction. And so I still continue to have a positive direction here. And 0.17 times 0.4 gives me 0.068. Now, what is the momentum of the two ball? Again, I need to do mass times velocity. It did tell me that the two ball has a mass of 0.17, but then the velocity I actually don't know. I don't know the speed of the two ball. In fact, that's what it's asking for, right? It says calculate the speed of the two ball after the collision. So I'm actually going to call that the speed of the two ball after the collision. I'm going to call that V because that's the unknown. I should always have a variable for the thing that I'm looking for. So that's what I'm looking for. And so now, after the collision, I'm going to have a total of that 0.068 plus that 0.17 V. Now this one has a V in it, that one does not. So those are not like terms. I can't put those together. That's why I've separated it with the plus. However, I do know that the momentum before should equal the total momentum after. All right, so I'm going to rewrite this as 0.459 is equal to 0.068 plus 0.17 V. And so now I just have to solve, right? I'm going to subtract that 0.068. And I'll get 0.459 minus 0.068. And I get 0.391, which is now equal to that 0.17V. This is just normal algebra. Now we're going to divide by the 0.17. And when I divide by the 0.17, I get that V is equal to 2.3 meters per second. There we go. Woohoo! All right. Now, letter D. You should have calculated that the two ball has a speed of 2.3 meters per second. Yes, we did. Yay for us. Woo! All right. Now, it says use this information to fill in the table below for kinetic energy of the balls in the system and determine how much energy was lost. All right. So we know that before the collision, the cue ball had 0.620 joules, right? We calculated that up here in part A. We know that the two ball has 0 kinetic energy because remember kinetic energy is 1/2 mv squared. So the two ball before wasn't moving. So when we put that 0 in, we're going to get 0 for the kinetic energy. So I add those together. I get a total of 620 joules of kinetic energy before the collision. Now after the collision, I'm going to have to calculate those. So it's 1/2 mv squared. So 1/2 times the mass, which remember was 0.17. Now the speed of the cue ball was that 0.4 squared. So 0.5 times 0.17 times 0.4 squared. And I should get 0.01. I'm going to go 4. I did these to the thousandth place. All of these I did to the thousandth place. So I'm going to go ahead and do that one to there. And then I'm going to do the same thing for the cue ball, which is 1/2 times 0.17 times its speed, which remember that's what we calculated here was V, which was the speed of the two ball. So that would be 2.3 meters per second. And so I can actually, on your calculator, you can go up here and you can just kind of arrow over to that 0.4 and hit delete, and then you can type in that 2.3. And so it's actually, I'm going to teach you a little bit of calculator stuff as we go. And when you push enter, it'll give you the new value, which is 0.4. Well, it says 496, so I need to round up. So that's going to be 450. Now, when I add those together to get the total kinetic energy, I'm going to add the 0.450 plus the 0.014, and I get a total energy of 0.464 joules. Now, obviously I've lost some energy. The question is how much was lost. So to find out how much was lost, it's always usually best to find the change by doing the final minus the initial. That's how you find a change. So I'm going to do that 0.464 and I'm going to subtract the 0.620. And when I do that, then I get a change in the kinetic energy of negative 0.156 joules. Now the negative just means that it was lost, which we knew it went down, and the 0.156 is how much energy was lost. So there we go. We've answered letter D. Let's move on to the next question. More fun ahead. Letter E. We say energy was lost. But we understand that energy is not really ever lost. It just gets lost to the system. It has to go somewhere. So thinking about those two balls running into each other, where could the energy go? Well, hopefully one of the things you're thinking of is sound, right? We talked about how sound has to be created by sound waves and energy has to get to your ears. And when it gets to your ear, then you can hear it. But that requires energy. So that energy comes from somewhere. Some of your kinetic energy gets turned into those sound waves. All right. You might be able to say that some of the energy goes to heat. That's usually the case in collisions, is that some of your energy goes to heat through the movement of the particles and things like that. And you could also say just the normal vibration of your balls. If any of the vibration, instead of being forward, if any of the vibration between those goes sideways or up and down, then you're going to lose some of that forward kinetic energy that we were talking about before. And so some of the energy could go into the vibration of that energy there. Okay? So that's letter E. Please do not use the other one. We did talk about in class that sometimes there's something called deformation, or when it changes shape, when you break those bonds and bend, the shape. That's not happening here. The balls don't change shape when they hit each other. They bounce off each other. And even if there is a slight amount of change, they go right back to what they were after they've collided. So there's no permanent deformation, no permanent damage here. Okay? Letter F. Based off of your results from letter D and your observations, what type of collision is this? Well, it is an inelastic collision. Remember, we had 4 types of collisions. We had elastic, which is where the energy was conserved, the kinetic energy was conserved, which that was not the case. We lost some here. We had inelastic, which is where energy is lost. We had completely inelastic. Completely inelastic is energy is lost and the two objects stick together. So that's obviously not happening. And then we had the superelastic. And superelastic was when you ended up with more kinetic energy than what you started with. And that obviously doesn't happen here. So inelastic, for the reasons that I just stated. I'm not going to write it down. Let's move on. Using Newton's laws, describe why the cue ball slows down and the two ball speeds up. Well, we know that the cue ball comes and it hits that two ball. So that should make sense. When the cue ball hits the two ball, it exerts a force on the two ball in this direction. And Newton's second law states that if there is an unbalanced force, the object will accelerate. So that's why the two ball speeds up. Now, Newton's third law states that if the cue ball exerts a force on the two ball to the right, then the two ball exerts the same force back on the cue ball in the opposite direction. So whereas the two ball feels a force forward, the cue ball will feel a force backwards in the opposite direction. And so therefore, if you are moving in this direction and something starts pushing you that way, you're going to slow down. You may eventually head back in that direction if the force continues, but the first thing that has to happen is you slow down and then you can go the other direction. So why does the cue ball slow down? Because Newton's third law says that there must be a force pushing back in the other direction. Therefore, again, according to Newton's second law, there must be acceleration in that direction. When your velocity is to the right and your acceleration is to the left, you slow down. That's it. Next, curling. I don't know if you've ever seen curling before, but in curling, it's just like this. They run along the ice. They hold what's called a stone. This is the stone. And as they slide along, they hold it for a little while. And then at some point, there's a line where they have to release it. And usually they give it a little bit of a push, with just enough push so that the stone ends up in a certain place. They're trying to knock away the other team's stones and get their stones closer to the center of the target. There's a bunch. This is not shuttlecock. This isn't the one with the sticks that the old people use on a cruise. This is a little bit different. But she's going to slide along with it at a constant speed, and then she's going to give it a little bit of a push to give it a higher speed. And that's what we see here. They're both moving with 1 meter a second, and then she pushes the stone so that it now has a speed of 2 meters a second. Now, this is not a collision per se, but it is an interaction between her and the stone. So that's going to be important as we go forward. Letter A, calculate the initial momentum of the curler as well as the initial momentum of the stone. Now, it does remind us that momentum is a vector, so the direction matters. So the direction of the velocity and the momentum both need to be negative. So remember, momentum is equal to mass times velocity. So we're going to take the curler's mass. So to get the momentum of the curler, we're going to take her mass, which is 50, and then multiply it by her velocity, which is 1 to the left. So we're going to go -1. And we can calculate that just to be -50, again, kilogram meters per second. The momentum of the stone is going to be equal to its mass, which is 18, times its initial velocity, which is -1, which will give us -18 kilogram meters per second. And just like that. And we now know the initial momentum of both the curler and the stone. let's move on to the next page where they're going to ask us to make the table. And eventually we want to find, well, in part C, they're going to have us find the speed of the curler as she pushes a stone. But right now, we're just going to use V for the velocity of the curler after she pushes it. So momentum of the curler, we just calculated that she had negative 50 to start with and that the stone have negative 18. So the total before would be negative 68. We've got that. Now, after the collision, the curler we still want to do that momentum equals mass times velocity. So the curler will have a mass of 50, and then it tells us to use V for the velocity of the curler, because in the problem, remember it stated that the stone now has a velocity of 2 meters a second, but it doesn't tell us how fast she's going. So we don't know. We're going to go ahead and put in a V. She can't be going 2 because it doesn't make sense that the stone speeds up and she speeds up, because where would that energy come from? All right. Now the stone has a mass of 18, and now it has a velocity of 2, still to the left, right? It says velocity of 2 meters a second to the left. So still to the left. So we go ahead and put in a negative 2 there. So that's going to be negative 36. And we add those two together so that we get 50V minus 36. You could go plus negative 36 if you wanted, but it's plus negative is the same thing as minus. Now, that fills in the table. So we've completed the table. That was part B. And the next thing is we want to do part C, which is to actually calculate the speed. Well, remember that momentum is going to be conserved as long as there's no outside forces. In the question statement, it did tell us that we could assume that it was frictionless ice. So we're going to go 0. Okay, or sorry, we're going to make those two equal. So we're going to say the negative 68 must be equal to 50V minus 36. And then from there, we should be able to calculate. So we're going to take that negative 68. We're going to add the 36 to both sides. We need to move that over. That'll give us negative 32 equals 50V. And then we're going to divide by 50. And we should get that our final V is negative 0.64. Now you'll notice two things, hopefully. First, you'll notice that she's slower than she was before. Remember, before her speed was negative 1 meter a second. Now she's negative 0.64. She hasn't changed direction. That's the second thing I want you to notice, is that she hasn't changed direction. She's still moving to the left. She's just moving slower than she did before, right? Pushing the stone doesn't mean that all of a sudden she starts speeding backwards, right? Now, the next thing it wants us to do is use the principle of Newton's laws to explain why it makes sense that she should slow down. Well, similar to the last question, Newton's third law says that as she pushes on the stone, we recognize that the stone is accelerating, right? The stone went from negative 1 meter a second to negative 2 meters a second. So it's speeding up. In order for that to happen, she must push on it. Now, Newton's third law says that if she pushes on the stone pushes back on her, which means that she then needs to slow down. And so therefore, we get our slower speed. Makes sense. Again, I'm not going to write it all down. I just talked through it. You can write that down on your paper. Now, because it does say explain. Saying Newton's third law is not enough. You need to go through the whole explanation that we just went through. Using the principle of conservation of momentum, explain why it makes sense that she should slow down. Well, remember we talked about that there's two ways to look at conservation of momentum. One way is to say before has to be equal to after. The other way is to say that the change in momentum of the curler has to be equal to the negative change in momentum of the stone. Or in other words, if the stone gains momentum, she should lose momentum. If the stone loses momentum, she should gain momentum. So conceptually, it's just they should both have the same change. It's just one's going to increase their momentum, the other one's going to decrease. Now, when we look at the stone's momentum, it goes from negative 18 to negative 36. So it actually loses or gains negative momentum. You can look at that either way you want. But either way you look at it, the curler then has to do the opposite. If her momentum increased in magnitude, then the momentum of the stone increased in magnitude, therefore the curler should decrease in magnitude. The way for that to happen would be for the speed to become slower. So there you go. Hopefully that makes sense with the conservation momentum. And again, you should explain it here. Don't just write what I've written. You should write down the idea of the stone's momentum, at least the magnitude has increased, therefore hers should decrease. Or this became more negative, so hers should become less negative. Either way is fine. Okay? Now, letter F, I'm going to leave that to you. You make your guess. Go ahead, see if you can justify, give an explanation. On the next page, we're actually going to go through the calculations that allow us to finish that. So, hopefully you've taken a chance to give your own guess for letter F. Let's have a look at letter G now. So in letter G, we want to find the kinetic energy of the curler and stone before and after the collision. Remember that kinetic energy is just that 1/2 mv squared. So the curler will be 1/2 times her mass, which was 50, times -1. But the reality is kinetic energy, you're always going to square your velocity. And so you don't really need to put velocity here. You can just put the speed. You can just put 1, and it'll give you -1 squared is +1. 1 squared is +1. So it really doesn't matter. But we can go ahead and do that. So we'll go 0.5 times 50 times 1 squared, which is going to give us 25 joules. Do the same thing for the stone, 1/2 m, and then times the stone's initial velocity, which again was -1. So 0.5 times 18 times 1 squared, which is 9. So we add those together, we get a total energy of 34 joules. You can check that out on your calculator if you want. 25 plus 9 is 34. Now we'll go ahead and look at after the collision. So 1/2 times her mass, which was 50, times her speed, which we just found was -0.64. Look it up on your paper, or you can actually still see it on my calculator here, squared. So 0.5 times 50 times -0.64 squared. Now it is going to do the squared first, so it's going to follow PEMDAS. I am going to just go ahead and get rid of that negative there because it's not really necessary. So I do get 10, I'm just going to go 10.2 joules, and then I'll do the same thing for the stone, 1/2 times 18, and then remember its speed was 2. Again, you can check back at the previous page if you need to. So 0.5 times 18 times 2 squared, which should give us 36 joules. We add those together, and we get a total of 46.2 joules, and you'll notice that we end with more than we started with. So, in answer to part F, what type of collision is this? Well, it is super elastic. That is super. Why is it super? Because we ended with more energy than we started with. All right? Now, the question is, how? How did we end up with more energy? Well, if you think about it, if you go back to the picture, remember, she's sliding along the ice. They're moving along together, same speed. What has to happen in order for this stone to move forward? Well, she has to push it. But in order for her to push it, what has to happen? Well, her muscles have to move. Well, how does that happen? Well, she ate some food, right? So the food, the protein, the energy that she got from the food, that is stored somehow in her body. Usually we call that some type of chemical potential energy. And that chemical potential energy, she is using to convert it into kinetic energy. So is there new energy? No, there's no new energy. But remember, what we're looking for here is we're looking for the kinetic energy. So is there new kinetic energy? Absolutely. If you were to add together all the possible energies, you should end up with the same beginning and end. But right here, we're just talking about the kinetic energy, the energy of motion, and we end up with more than we started with because she turned some of her chemical potential energy from the meals that she ate over the last couple of days into the kinetic energy of the stone going along. All right, so there we go, a super elastic collision. Next up, American football. So this is our last question that we're going to try to get through. We've got two players. We've got a running back that's carrying the ball, moving forward at 1.9 meters a second. And then you've got a linebacker that's going to come in and try to attack him. He's going at 1.6 meters per second. All right. Now, in the question, it says Wagner will wrap up completely so the two players stick together after the collision, right? And that's what you're taught in American football and probably in rugby and other sports, is that when you tackle somebody, you should wrap up and grab them so that you travel together after that. Now, hopefully that's making you think about a completely inelastic, okay? It won't stick together and be super elastic or elastic. If it sticks together, it's going to be completely inelastic because it takes some energy to be able to hold them together. Some energy has to go into that bond there somehow. All right. Now, based off your choice above, what can you conclude about the energy of the system before and after? It needs to lose energy. That's what we were just talking about. All right. So hopefully that's what we see. Let's go on. Determine Jonathan Taylor's momentum and kinetic energy before the collision. Well, Jonathan Taylor, it says, has a mass of 102 kilograms and is running at 1.9 meters a second. So for his momentum, we're going to take the mass, which is 102, times the velocity, which is 1.9, and we go 102 times 1.9, that's a 0, 1.9, and we get momentum being 193.8 kilogram meters per second. The next is kinetic energy. So for kinetic energy, we're going to go 1/2 mv squared. This should be getting kind of normal by now. You should be comfortable with this. So 1/2 times his mass, which is 102, times his velocity, which is 1.9. So 0.5 times 102 times 1.9 squared. And we get that he has 184 joules of energy. Now it is 0.11. That's close enough. 3 digits is good enough. So kinetic energy is 184 joules. Momentum is 193.8 or 194 kilogram meters per second. The next question is determine Bobby Wagner's momentum and kinetic energy before the collision. Notice that velocity and momentum are vectors, so direction matters. So the negative is going to be important for our momentum there. So our momentum, again, will be that mv. So the mass was 110. His velocity was 1.6, so 110. And then we need the 1.6, but it is going to the left, right? In the drawing, he's going to the left, so we're going to put in a negative 1.6 here. And so 110 times negative 1.6 should end up giving me negative 176 kilogram meters per second. All right. Now the kinetic energy is going to be 1/2 mv squared. And so again, 1/2 times the 110 times the negative 1.6 squared. So 0.5 times 110 times 1.6 squared. You notice I didn't put it in negative. We talked about that in the last question. So we should get that the kinetic energy is 100. I'm going to go ahead and round it just like I did that one. So 141 joules of kinetic energy. All right. Now it wants us to do the momentum table. Okay. And we're going to use that to solve for the final velocity of the two players. Now remember, they're stuck together, so they should end up having the same final velocity. So Jonathan Taylor before had a momentum of 193.8. Bobby Wagner before was 176. We add those two together. Yes, the negative is important. So we go 193.8 minus 176, and I get 17.8 kilogram meters per second. I know I'm not writing that down every time. You understand that each time we get momentum, it is the same units there. Yes, it doesn't have a lot because one person's going one way, the other person's going the other way. So the sum of those two is much less than what they would be individually, right? It's like when we did velocity and displacement before, right? You went to the right and then you went over to the left, and your final displacement was less than either of your previous distances, right? And so that's what's happening here. Your total, the result of putting these together, is less than either of those individually. Okay, so now we do after the collision. So Taylor, remember, had a mass of 102, and then this is momentum, so times his final velocity, which we're going to find. Wagner was 110, that was his mass there. He's also going V, and so now we can add those two together, so we'll end up with 212 V. This time they do both have V because they're traveling the same speed, so we can add those like terms together, and this then should be equal. And then at this point, we should be able to just solve that. That's 17.8 equals 212V. Divide both sides by 212, and we get an answer of 0.08. I'm just going to go 84 meters per second equals V. Now, hopefully that kind of makes sense because one guy's going this way, the other guy goes in that way. They ram into each other, and this guy is going to cause him to slow down, and this guy is going to cause the other guy to slow down, and so they should end up with a pretty slow velocity at that point as they collide together. All right. Now, we are ignoring any other frictional forces or them pushing off the ground and all that. We're just trying to keep it simple here, trying to make sure that we're understanding the principles before we do anything too complicated. All right. So there you go. Now, with the information from part E that we just found, we're now going to complete the kinetic energy table and determine how much energy was lost. Now, this one didn't even get a choice. We already know energy was lost because remember in the previous question we said it was completely inelastic. We know it's going to lose energy in this process. And that should make sense. They're both going really fast, and at the end, they both have a really slow speed. They're both going really slow. And so there's obviously a lot of kinetic energy being lost there. That's how bones can break, and that's why you need padding, is because you have all that energy that has to go somewhere. The padding helps to absorb some of that. All right, so here we go. We've got the kinetic energy of J. Taylor would be 1/2 times his mass. Oh, we actually already found this, right? It was 184. So I'm going to go 184 joules. And we know Bobby Wagner's before, which was 141 joules. So we add those together and we get 325 joules of energy at the beginning. And then afterwards, we are going to have to calculate this. So 1/2 Taylor had a mass of 102 and a final velocity of 0.084, and that's squared, 1/2 mv squared. We'll do the same thing then for Wagner, which is 110 times 0.084. They're stuck together, therefore they travel at the same speed. So I'm going to go 0.5 times 102 times 0.084 squared, and I end up getting not very much, which is 0.3. I'm just going to go 0.36 because the 9 would make that round up. If I wanted to round this one, I'm going to have to round that one too. So I'm just going to go 0.36. And then we do the same thing there for Bobby Wagner, but we're going to go ahead and change the mass to 110. So 1/2 times 110 times the speed, 0.084 squared, and we get 0.39. And we add those two together, and we get 0.75. Now, you'll notice that's a pretty big change in energy. That's why it's so loud when they smack into each other. So the question is, determine how much energy was lost. So I'm going to take that 0.75 and I'm going to subtract the 325. And so essentially we lose almost all of the energy, which would be 324.25 joules. There we go. That's how much energy is lost. You'll notice I got a negative. That's representing the fact that it was lost. Okay, now we move on. The last question here that we're going to look at, I'm not going to do the challenge today. We know the energy isn't really lost. It just changes form or goes somewhere else. Name at least 2 places where the energy could have gone. Okay, well, we talked about this before. It could go to the sound. Okay, in this case, realistically, there is definitely some friction with the ground. So it could have gone to tearing up the grass. It could have gone to heat. Okay, so we're going to go ahead and put heat there. It's probably not going, well, I guess it could deform the people. If a bone breaks or something like that, that's literally what's happening, is that the energy, that kinetic energy, is being transformed into energy to break the bonds of those bones or whatever else. So that's a possibility. That's why those sports are, as dangerous or as exciting as they are, is because there's a lot of energy going into that, and that energy's got to go somewhere. Sound, heat, vibrations, deformation if something gets hurt, right? It could be as something as simple as, a bruise, breaking blood vessels, right? All of those possible ways is places that the energy can go into. All right, so there you go. That's the end of this worksheet. I hope that's helpful in answering some of those questions if needed, and I hope to see you in class.